Yeah, right here.
So since we're not sitting completely in silence, anyone who's working or working about working at Boeing, you want to raise your hand. So lots of Boeing representation.
I need to raise my hand.
How long have you been at Boeing?
Almost 7 years.
7 years?
Yeah.
Where did you work prior to Boeing?
In graduate school.
Oh, okay.
I was University of Memphis.
Memphis?
Yeah.
Oh, okay.
Usually work for Boeing and same program like Christian or like.
Yeah, Lisa and I are still current employees. Josh used to work at Boeing, and then this is a future employee.
Yeah, Luke,
Yeah.
future employee in Seattle.
You interned at Boeing?
Yeah, former.
I'm Northrop, so.
Ooh. He's taking next. Where's the notebook?
Ex-Northrop. I'm not going back.
I'm really excited to see this because I'm taking my first ever ML class this semester, so I'm excited to see something, a real application of it. I probably won't understand all the details,
Yeah, that would be good.
Yeah.
Yeah. There are several problems we can apply them. So
yeah, definitely.
it's just a preview. So what's the typical format? We interact as we talk or present and talk?
It's up to you how we would like to do it.
Yeah, I think we can ask questions anytime. So I don't need to fix my whole content. It's already there. The important is to have the interaction and understanding. Right? So,
And the speaker is also allowed to take up the map.
the audio.
Well, since we all can be here, we'll go ahead and get started. Thank you so much, everyone, for joining us today for another Milo talk. We are very happy to have Dr. Nobal, who is an associate tech fellow at Boeing, specifically in Boeing research and technology, we involved in artificial intelligence. Nobal is a PhD in computer science from the University of Memphis, has spent time in both academia and research labs, including Microsoft Research, AT&T Labs, and has over 45 publications, including nods for Best Research Paper Award. So with that, I'd like to hand it over to Nobal.
Yeah, thank you, Christian, and the Vivo team for inviting me here. I'm really excited to share this topic in front of you, and we are already connected to Boeing, so I think you probably taught some part of it. So I'm really excited to be here. Before I start my talk, I would like to give some acknowledgements and some references. So, so we published some papers with my colleagues, Daniel White and Nkao. And these are the papers that I listed here. So I will be covering most of my talk from these papers. So if you have any questions or if you would like to deep down, more in any of these topics, you can go to these papers and read it. And the good thing is in Boeing, like we cannot present the things that is not public, right? So these things are already published papers. So that's good for me to cover. Okay, so basically today I will be covering these topics. I will talk about maintenance records and like why those are important for us and what we can do with it. And I kind of take like 1/3 of this time talking about maintenance records and the values that it can give us in Boeing and other manufacturing companies. And then I will talk about the knowledge types, the things that we can get in these maintenance records. And some machine learning and natural language processing techniques that we can apply to leverage these records. And in that, I will talk about the different challenges and different novel approaches that we have developed to solve those problems. And I'll cover around 2/3 of my time on those topics. And I put like the question answer at the last, but it's informal, so you can ask any questions anytime. So here's the thing, like part data plays a key role in vehicle health management. And like for effective and analysis of data is needed to diagnostics and health management of vehicle. And we call here vehicle because this is not only for Boeing kind of thing, right? It can be for any other auto industry as well. So a wide range of data can be used for this purpose. We have like sensor data that records faults, and those faults are about like system issues, LRUs kind of thing. And like sensor data reports this kind of faults, but there are other records like crews or pilots or mechanics, right? They write this kind of data into text form, which contains like a lot of information, richer information, than the sensor data. And it's harder to analyze because these are in written text, right? And we will show some of the example later, like how messy they could be and what are those challenges, right? So this part-related information is in the free text data we want to leverage, but it's not easy like the sensor data, which are in a very structured form, right? So I will be talking about how machine learning and natural language processing can help us to decipher or to mine those knowledge. So talking about maintenance records, these are the records corresponding to planning and recording of preventive, predictive, and emergency maintenance activities. And like in case of aircraft domain, like these are the logs, day-to-day logs from the in-service aircrafts, and they have a lot of part information like issues, or conditions or different kind of situations mentioned there. And there are a number of maintenance data types inside the aircraft domain. One is called the logbook. Like as soon as the plane lands in the airport, there is some checking going on based on those sensor faults to see what can be fixed so that we can operate instantly there. And like there are pilot logs, and there are like crew logs, as well as the logs from the mechanic who actually report and solve these problems, right? So those are the logbook records. And we got these kind of records from our airline customers and government customers around the world. And there's the schedule interruptions. Like if there's a significant delay on the schedules, then we have different kind of data processes that records these maintenance records. What was the issue? What went wrong? How we fix it? Those kind of things, right? Another is the component removal. Like when anything is removed from the aircraft, we have an event. We need to record that. And we fix it, we replace it, or maybe reinsert a new one, everything is recorded. So that's on the component removal side. And the activities in the shops are recorded into the shop data here. So these are some examples of, maintenance records. And the common thing is like, there's an issue reporting side where people report the issues. And then, something is not working kind of thing. And there are resolution side where, oh, I fixed it, or I couldn't fix it. I postponed it for others. So the commonality among is like that. So we have issues, those are reported, and we have resolutions, which, after those fixes. And I talk about this too because each of these data type has different kind of information. So which we'll be talking about. So these are the sample records. These are the actual records that we got from mechanics and around about aircraft maintenance records, right? And I want to spend some good amount of time here because this shows the problem challenge that we need to face. That way we can frame the solutions, right? First of all, like you can see the numbers are written on the left-hand side. So as soon as we get these kind of reports from airlines or government customers, then we have the corresponding code, the ATA code we call in commercial side, assigned to that. For the military side, we have other codes, but those are pretty similar to this one. The 52 here is about doors. If any issues coming with doors, then we assign the code like the ATA 52. And if anything about, landing gears, those are assigned to 32, 32. So these numbers are here, and you can see there are words with a lot, different colors, right? And these are actually the values that we would like to give. And those are a lot, right? So it's very rich in this knowledge, part-related knowledge. We have part names like DORR, which is door, and we have handle, cover, spring, right? These are part names. And then conditions is weak, no output, right? And want to limit. These are the conditions of those parts here. And locations, like there could be parts in different locations, and there mentions about that. And we can see some of those instances here too, right? Like number 7, gear number 7, something like that. So, and actions, right? Different tests performed on those, and then those are recorded here. So when I earlier mentioned 2 buckets, one is the issue side, and one is the resolution side. When we see the records on the issue side, these are mostly from the issue side, where they report about what's going wrong, what are the problems, what are the parts, what are the location, kind of thing. Versus when they do the resolution, then we have, of course, the part names and others appear, but also appears is the actions, what actions they do, what kind of tests they do, and what are the results of those actions. Those are found on the second, the resolution side. So we cannot combine these two and then make algorithms for that, because they have different kind of language. So in summary, as you can see, like so much acronyms, abbreviations, right? Like BPCU, right? It's add up. People most of the time they write, but they can create themselves too.
Is the ATA specified in some sort of form from the customer, or is that determined by the actual description of the text?
So the ATA stands for like Air Traffic Association. They have defined the code from 0 to 100, and these represent like system and subsystem information. Like 52, anything about 52 about door, right? So we get these records from airline customers who themselves assign these numbers, but not always correct, because here has issues. Maybe it's just something different, right? So those are the numbers designated to the system and subsystem level. And we have like in landing gear too, maybe there are sub level like 3201. They have even subcategories of that, but I'm just showing like the top 2 digits here. Thank you. Any questions so far? So now we saw maintenance records, right? We saw different issues there, like acronyms and others, tweaks kind of thing. It's a different language, right? And these are not known by the outside academia, because these are inside industry, waiting for you guys to help us, right? Now, if we come to the natural language processing, we call knowledge here, right? And what kind of knowledge? And those knowledge are kind of called entities in natural language processing. And I'm listing here some of them, like part names, and then part numbers, locations, conditions, maintenance actions, and the results of those actions. Right? These are the different kind of entities of interest that we can see in those kind of records. And then once we find these entities from this, then there's other kind of information we need to do, linking, right? We extract part names, but we also extract location. How do we associate that? That problem in natural language processing is called the relation extraction, like linking one entity to other. So basically, when we talk about mining knowledge from this kind of records, we are talking about mining these kind of entities and the relations. So say we solve this problem, right? We have these records, we have this knowledge of it. What we can do out of it? Then we have, we can use them for improving the reliability and safety, while minimizing the operation cost, and we can facilitate the fix effectiveness. Like if we make a fix, how long it lasts, right? Is that a good fix? Those kind of things can be studied by, leveraging this knowledge. And like efficient sourcing mechanism, like if we want to see what are the problems in landing gears that we are seeing, right? So we can choose the landing gear knowledge and then see what are the things about it. So all those analyses are enabled here. And we can see what parts are performing well And we know these parts are supplied by certain suppliers. Maybe those are the thing we need to consider, right? It has a lot of link among different data sources. And we can see what kind of failures, what is the frequency of failures. We can easily compute with those knowledge. You can see the trends over time. And again, linking multiple data sources from supply chain to manufacturing to our all other sources, right? That gives us the bigger picture of the system. And overall, the goal is it improves the reliability and the quality of the products and services that we offer. And for airlines, it's about improving the schedules, and for flying public, like good schedules are good, right? Now, so far we talk about like the maintenance data, and then the knowledge types that we can extract from that, different like entities and relations, and the values that this can give us, right? Now let's talk about the technical challenges. So what kind of technical challenges we need to face in order to process or mine this kind of knowledge? I will be talking here about that. And for any kind of knowledge that I mentioned earlier, these are the challenges. And I'll be talking about some specific challenges for part names and conditions later on. But these are the overall challenges that we want to mine from those has to face. Like volume and variability is there. We receive like tens of thousands of logbook records every day from our airlines and government customers. And those are from like non-English speaking countries or English speaking countries. And as you saw in the earlier sample, they have full of typos, ad hoc acronyms, abbreviations, word concatenations, and word splits, right? And at first we thought like maybe countries with non-English speaking would type, not good English. But in fact, in many of them, they type good English, they are more careful about writing versus like English speaking countries, they do pretty fast and they want to get it out done, So those kind of things we observed there, right? And the other thing I noticed, like the door was probably the simplest word to write, DOOR, right? And I don't think people make mistake. I did not think people make mistake, but looking at these millions of records, I found like even the term door can be like more than 50 different forms, like DR, DOOR, OOR, all sort of things you can do. And mix, also, merging with all the concatenating with the neighboring words, right? All variants you can find there. It's very, very messy, right? And like CRG for cruising, nobody knows unless you see it, right? So it's very ad hoc. And so this is like volume and variability, right? That's the topic here. And the other is unique extraction problem, right? So part knowledge extraction is a problem like it's not studied much. We are among the first groups who actually investigated this problem utilizing the latest techniques to mine those, which also means a good thing for us because we are approaching that for the first time, but with challenges, we don't have like resources that we can leverage from others, right? And so in natural language processing, mining like person name, location, organization is pretty standard. Everybody would love to do that, and it has a lot of values, which means it has a lot of knowledge we can leverage for those by academia and others. Like WordNet and Freebase, these are the common resources that we can utilize for that. But in our case, we cannot leverage that because it's a unique problem in the industry. And for any machine learning solution that we develop, the problem is we don't have the training data set of that, right? We get it and then build a model. It's not easy. We don't have that. But what we have is we have vast amount of records. This is not labeled. Maybe we can utilize that, and actually we do that. I will show that how we do. And like, so the typical approach is, let's create the training examples, right? We annotate these records so that we can use to machine learning methods to learn these kind of models. But like in our case, even that is expensive because this is domain specific data. Like, very few people know about that. We cannot go in the mechanical torque or something and then ask people, hey, could you help us to label? It's not possible. It needs more knowledge there. So some domain specific knowledge to annotate. So these are the challenges in general. Any type of knowledge we would like to mine has to face, we need to address this kind of thing. Now I'm talking about the specific challenges for part names extraction, which we'll be talking about after this. So part names are typically multi-word terms, and which contains a lot of domain-specific expressions, and it has a lot of variabilities too. And if we think about person name, maybe 2-3 words, maybe 4 words, typical, right? But part names, the longest one we discovered was about 12-word long part names, which is not like the person name or organization name, right? And this is one example, which is 6-word long part name. And also, if you notice, a sub-string of a part name is also a part name. Look at that, main landing gear. If you just consider landing gear, is also a part name, right? So here's some interesting observation we found here. And different suppliers have their own nomenclature for the same part, right? How do we address that? It's not the person called everywhere the same way. It's like that, right? The same part can have different names used by different suppliers and operators. And one thing is could be maybe, why don't we have a list of parties? We collect them and then try to use that to mine, right? And it's okay, that's not a bad solution. But the problem is we cannot maintain it because part names have different things upcoming, one. And there are a lot of issues with typos and others, right? And it does not give the whole picture because things are evolving. So we need to be careful on that as well. So these are some specific challenges that we need to face in extracting part names.
Could you force the data to be clean by changing the way they enter it into the system? So instead of having a free form text field, you have drop down menus and things like that, like a field that would say the part number,
right?
So that's the part number, so you don't have to figure out what it is.
That's one solution. But in practice, people want to do job done fast. And then first of all, developing that kind of technique takes time, right? We are already in the techniques utilizing back in the days, right? So ideally, if we have way to select those things, that solves some part of this. But even when you force people to write that way, you cannot get the full information. Writing in the natural form is so much powerful. We can write a whole bunch of information, which you probably would not cancel it from things, right? So definitely that's the one that makes life a little easier, but we cannot avoid the free text ones. Yeah, good question.
So how long are the text that you're trying to extract these part names from? So are they usually very distinct description of the problem, or could they be paragraphs of text that give you a lot of context about what happened?
Mm-hmm. As I showed in the previous sample, those are from the logbook records, which are pretty much short, 2 sentences or 3 sentences, can go up to 5 or 6, but not too long. But we do have other data sources like Boeing communications, for example. We frequently communicate with airline customers in emails, which are long, right? So our techniques here can be applied to any kind of data sources, especially the part name extraction, which I'm going to talk.
Maybe you'll get to this, but if an acronym could actually mean either two different parts, or maybe a part and an action or something, does this method also address training by context of the other words around it?
Yeah, I think that's one typical problem in natural language processing, because you have the same term can have different meaning depending on the context, right? So I would talk about that, latch, for example. Latch could be a part name or could be a verb, right? Depending on how it is used. So we need to address those kind of issues too. Yeah.
Do you have any external issues that you're doing here besides the
Say that again.
do you have any other sources of data that you can besides the text logs, any sort of database of partial questions or full questions?
We have not utilized that, but we can utilize it because there are some ways we can use as a features, for example. Yeah, I'll be talking some of that in the coming slides. Yeah. Question?
I just want to ask if it's for a specific aircraft or how small.
That's a good question. You guys are asking questions before even I present. So yeah, so ideally we like to have fewer models, right? If a single model works for all, aircrafts, that's good because we have very few models to maintain, right? But this part name extraction works for any model, actually not in military as well as the commercial side. And for certain may not work. So always we are looking for solutions which are agnostic for practical reasons so that we can maintain fewer effort. So
As opposed to these documents specific. Like.
yeah, so I think it depends on like which one can be solved that way, which one cannot be solved, right? But yeah, we can try it that way too. Okay. So I want to spend a good amount of time here because we find an interesting approach. We discovered this technique, a framework called PANDA, part name discovery analytics. And this is about for the extracting part names from these text records, right? And we have patented this technology already. So what it does is it leverages linguistic domain knowledge and NLP techniques to extract part names. So it can extract from any models or any data sources. Those are about part names, right? So we start with, it goes in the loop, right? We always start with the seed heads, which is step number one. Like if we start typing this part type, we can easily come up with fan, relay, bulb, switch, kind of like that, right? It's so pretty fast, right? We can get this basic part name, part types, which we call heads in linguistics there. We can come up with this basic one initially, right? So that's the seed heads. Then what we do is, these are as you see, single word part type, right? Like and bulb, like that. So we can use this part heads to extract longer part names. Because as I said earlier, we have vast amount of records, millions of records about parts, right? Then we can leverage that to get the longer part names. Like from PAN, we got trust reversal PAN. Because we can scan all our on-label data and then see these patterns, and we can get this one. And we applied the try approach. If I have time later and I can show how we can do that. But the idea is you form a tree where the root of the tree is the basic part type, and the words under them, like the children, are the terms appearing before that. So if you have fan, and if you look in all your records, then reversal fan is more common, right? Because that's the phrase we can get. So we have a technique based on that try, which basically takes the seed hairs and expand to the longer part. And we have a very good accuracy on that. So we started with that. We have now longer part names. What we do is that now there is a purification step in the number 3, because when we get from this try structure, this longer part names, there are some noise. We don't want to have part names starting with verb, right? So it is replaced, landing gear, maybe very common in the data. And then we mine from the step 2, replace landing gear is a part name. But we don't want to have that as a part name because it starts with the replace, right? So we have some purification steps that removes this kind of noise and generates those longer part names, right? Now, with longer part names, what we do is, as I said, we have vast amount of on-label data. We go through it and then find out where they exist, right? And here's one sentence where then examined engine fuel spare fault with some, right? So we found these longer part name appear in that sentence. Then we can compute the features, parts of speech tab, which are like nouns or words, verb or adjectives like that, for those sentences. And ultimately, our goal is to get the goal labels, because we have these tokens on the bottom, and we would like to get the goal labels in the top, which basically tells whether those are part of the part, right? Then examined is not the part. So we get O label. For each token, we need to give the label. O, and then we have bunch of part related tags, and then O again. So that is, ideally, if we want human to annotate, we would like to get records type. But in this sentence, this is the part name, and that's the label human assigns. So that machine learning can model can be trained utilizing this, in the example. Here, our process is automated. Our program can annotate and make this training example. So, which is a plus. Now we can, with this, we have a bunch of sentences like that. We can train this machine learning model. Here we pick the conditional random fields that utilize these parts of speech features and the text after and then text before of those partners, because those are the good signals telling about that. So that model now is able to predict part names, right? We build a model. Now we use that model to predict part names in the on-label text. And these are some of those extractions. Now, starting with, basic part names, longer part names, training examples, make the model, use the model to predict longer part names. Then, if you notice in these part names, the structure is that, why use parts of speech tag? Let me talk about it. Because if you look at the part name, those consist mostly of like nouns and adjectives, like engine, fuel, sparkle, right? All nouns here. And it doesn't have verb in it. Most of the part names do not have, actually, like 98% of the part names don't have verb in it. Like handle of the door, that kind of things do exist. But most of the time, it's either noun or adjective. For that reason, we use these parts of this feature. And when we extract these longer part names using the model, then we see that actuator was not initially in our list. Now we got the actuator, right? That we call the last, the head again. So in that loop, we extract part, purify part, generate the training example, build the model, we predict the part names, these are these, and we can purify using the same step like we did here, and extracted the head nouns, which is basically the last term in the part name. Now we can have optional approach step to see whether these extracted new part names are correct. Human can intervene and say, okay, this place seems correct. So I say it's a good head. If it's not correct, it's a bad head, or it's a borderline head, could be in between. So we can have like a human in the loop just before purify head nouns step, on that line. And that would mean like we got now more larger number of seed heads. We can start the same process again and again and again and impose that.
When you started this project initially, I guess how much of this did you map out versus like, you made some progress, failed on certain aspects of it, and then changed course? I guess was it just yeah, that's
yeah, I think that that's a good question, right? So when you build machine learning or NLP model, we start with something and then try to see, right? And here too, like we were debating, should we use the parts of speech features, right? Because it's so noisy, right? Parts of speech tagging in noisy text is a challenge. And should we use that or not? Let's try, and it worked. And then, we have our specific parts of speech tagger, and then, oh, that's gonna work, and then we always adjust like that, to see. But the one challenge, as I mentioned before, is we don't have a gold standard to test, like, let's make a change and then see if it works, because we don't have the test it available, right? There's the challenge. So we have to go through a little tougher road, but yeah, of course.
To validate one of the heads, are you like reconciling the information with the bill of materials, or like is that automated, or how much of that is human based?
Yeah, so what we do is, as soon as one head is extracted by this one, and we show the context. Hey, we found these sentences, 5 sentences, where these terms appear, and do you think this is a part head in this context? And based on that, the user judges. Yeah.
Is that feedback from inform any other participants besides which heads go on to the next generation, or just that decision was informed by?
Just that decision, yes or no? Because the goal is, if you recall before, we want to utilize less human input, because it is a very challenging to get the label data set, right? And by doing that only on the head level, it's so fast. Like I will show example right there. This is one snapshot of the run. We applied this Panda to 1 million data set with 1 million token in different data sources, like logbook data sources, schedule interruption, and Boeing communication system. And this is on the schedule interruption. You can see we started with 36 one, good hits. And then by iteration 7, we got like 317 good, 390 bad, and then 65 borderline. So the decision has to be made only on the head level. And it took less than 3 hours to do this one, and pretty fast. And you can see number of parts that we extracted from that is like a lot, right? So we spent like 3 hours or so, but we got like 10,000 parts already. So it hugely minimizes the need for human annotation.
Was that trial done with some kind of data cleaning? You're trying to expand acronyms and clean up words so that you actually get consistent unique tokens, or is this a trial that can even improve the results after?
Yeah, for these Panda experiments, we did do a lot of cleaning. Like we do have acronym expanded, right? And then we do have like CRG to cruising kind of thing. We have those kind of things. So I could not present today because we have not published that paper yet, but we have developed some techniques that helps to clean this text, this text pretty good. Yeah.
Just going back, when you talk about this logbook, is this logbook digital or is it like it is a combination of both digital and like a handwritten logbook that can be how are we worried about the data collection?
Even how the logbook look like?
Yeah.
Yeah, so yeah, I think this is one snapshot of logbook. I had initially like a bunch of sentences like, hey, this one does not work, or here is a tire has flat tire kind of thing, hey, like AC not working, or something like that. So those kind of things. Like that.
So my question was it digital or is it like record handwritten record?
Oh yeah, you mean like how they are? Yeah. So the one we received are already in text forms. Yeah. Any questions for that? So as you can see, like by 7th iteration, we got thousands of partners by this approach, and it's pretty fast. And we already applied these Panda techniques to other military data sources, and we got pretty consistent results, and we are already deploying these models there. And these are some of the extracted parts from that particular round. And as he asked the question about do we do cleaning, we do some kind of cleaning, but we may not have finished all the cleaning that you can see here too. And I will talk about some of the post-processing steps that we need to do in this later on.
Yeah, this is the Panda thing to deal with the inflation part, because we start with the head, but the head is not part of the
So, we have the machine learning system built on the Panda. If you look at that right there, right, predict part names. So when it predicts the part name, it utilizes the context, right? So say something like something is not working. If it's not working is present, then the word prior to is most likely is a part name, right? So that could be an acronym or abbreviation and others. So the idea of utilizing the machine learning here is to discover these kind of variations in the part name. And the human in the loop can say whether the extracted one is correct or not, right?
So that's what not.
So let's say like PNL appear like potential partner, right? And in the human in the loop, it says it's PNL is a partner, right? And we also provide context like left panel, left PNL, right PNL, kind of those context. And then humans say, oh yeah, looking at this context, it looks like it's a good hit. Or looking at this, it may not be a good hit. So we provide that, the context where the term appears for the human to judge whether that is a partner or not. So again, like we have these papers, like if I may not answer your question as you thought, you can always refer to our papers. We have the description there. Now, quality of extractions, right? We extracted these part names, like what they do, what are these good, right? So we cannot evaluate all 9,000 parts. And we cannot evaluate in terms of recall, like whether Panda is something or not. But what we can do is, we can randomly select some parts and then see whether those are of good quality, right? We can evaluate that way at least. So we extracted like, 1,000 parts and evaluated manually, and then we found like above 80% of them were correct. So that's what we came up at that time. So in summary, with the minimum human input, we were able to extract part names, right? Now we talk about different kind of knowledge, right? Like part names, conditions, actions, results, right? So we want to go beyond the part names, right? So that's where I'm going to talk about in a couple of slides. So we have like noisy text like that, and as our input, we want to build some machine learning model in the middle, and we want to extract different kind of part knowledge. Here I'm talking about parts and conditions in this illustration. So our model consists of these three layers, where we have like the input layer at the bottom, bidirectional layer in the middle, and CRF layer in the top. So in the lower one, if you say tire has flat tire, that is the input, and we map this word into the vectors, numerical vectors, that we're utilizing word embeddings. There are several word embeddings available in the NLP, like word2vec being one of the popular one. But in this experiment, we choose the fast text embedding, which basically can handle the terms it has not seen before. Like we saw a lot of typos and those kind of things, right? And the word2vec cannot handle with the out of vocabulary terms, whereas the fast text can handle because it relies on the subword information. So even if the panel is written, PNNL, something like that, still some component of it are related to the panel, right? Of course, it utilizes the context. So the fast text embedding appeared to be very effective for us here. So words, and we convert to the corresponding vectors, and those vectors are like providing inputs to the bidirectional layer. The idea of bidirectional layer is like when you say like left, light, not working, something like that, then the fact that not working appears in the last means that maybe something before is a part name, right? That's a good indicator that things before it might be a part, right? Similarly, like the term left in the front signals that maybe something after it will be a part, right? So there is a clue in the before and after of a part name. And utilizing like forward and backward, LSTM provide us this kind of clues to the CRF layer. So which makes the decision. So that's why we want to use the information from before and information after the word to predict whether that is a partner or conditional or not. So that's the framework we applied, and this is one of the common framework people apply in NLP to extract entities. And here it computes the feature itself. So we just need to have like the training examples, this input and the corresponding tag, like the first tire is a part, head is O, flat is, flat tire is part of the conditions. So it's kind of the label assigned to each token, right? So we want to make this kind of model that can assign parts or conditions or other knowledge types or O. From that, we can extract the knowledge. And these are the unique challenges for extracting part conditions. I talk about overall challenges, the typos and all kind of things there. I talk about specific challenges for part names. And these are the unique challenges for conditions. And conditions are multi-word terms like enough, broken, no output, too much cold air is coming out, is a lump. So there is not like a standard, length of those conditions. And a part can have multiple conditions. For example, here a door handle can be broken, difficult to turn, missing, loose, right? It's all kind of things there. And interestingly, like condition can include part name. For example, like West Service door, right? And like, has a defective latch, right? Defective latch probably is a condition here. And condition can be linked with the, involved with other entities like locations and others. And one of you talked about earlier that, how we differentiate, right? So their cockpit door lock will not lock. If you look at that, the first lock is a part of a part name, whereas second is not, right? It's the same word, but it has a different meaning depending on how it is used in the context. So those kind of things is always exist in the language that we have to face. And also, like, unlike part names where the most of those terms are either adjectives or nouns, and conditions do not have those kind of patterns. Now, in this experiment, we picked the 777 model and two ATAs, 32 and 52. Both are of different themes. One is for system, another is for structure. We want to see if the technique works for both kind of things. And our examples look like that. We have the tokens. We manually provided labels there. And then like generate these examples. We have like around 1,200 examples for both of the ATAs. So we mark like part names and conditions for this. Now, so here are the results. We saw the model, right? We saw that we got the training example by manually providing this information. And then now we train the model and for cross validation. Like for the training data set, we split into 10 different folds, which is 9 for the training and the last one for testing. And we did for all the folds here. So with that, we report results on the baseline, which is basically the lookup system. From the 9-fold, which means for training, can we simply do lookup and see whether those appear on the testing one, right? That's the baseline. Versus machine learning is the model. And we have part, condition, label, and both label. All granularities are provided here. As you can see, for ATA 32, that side, we got 84% F1 score for part, 74 condition, and around 84 command. And similarly, inside in the ATA 52, we have 81% for the part, 73% for the condition, and around 80%, 78% for the both. So kind of very interesting observation. We can see that like it shows partners probably are easier to extract than condition. And one most likely is because they don't follow any patterns like the part names, right? Where they have like adjectives and nouns. And conditions are harder because those are describing more, more diverse way than the part names probably. So this is a pretty good observation we got from that. Any questions here?
Did you do any fine tuning on the embedding model you used, or just use it as?
Yeah, that is in my future as I will show. Yeah. So you will probably be thinking, talk is over, but I still have some few slides to talk about, because we talk about different kind of knowledge that we like to mine, and we talk about extracting part names and conditions, right? And we can apply the previous framework for any kind of knowledge. We have training examples. It should work very well because that model is well known for extracting knowledge if we have those kind of examples. But I will talk about now a couple of slides in the text normalization. So extraction is one thing, but here is another thing we need to do, which is called the normalization, right? I'm showing here some of the examples, some of the cases. So first one, like air inlet actuator and air inlet door actuator. Do we consider them the same? Probably not, right? Because the second one is most likely an instance of the upper, maybe a specific of the upper, right? When there is a problem with air inlet door actuator, maybe it's a problem with air inlet actuator, because those are probably in the same hierarchy, right? So that's one kind of issue we need to face. And another is in the aircraft actuator and airplane actuator. We cannot consider them separate because they are the same, right? How do we merge them, right? We need to do normalization of those partners like that. In the third one, ENG, ENGI, NE, ENGI, and ACT. We need to combine this, right? So that we can do the accurate information from the text. So to solve that problem, we came up with a solution called Unimer. This is one of the papers that we published. What it does is it's a machine learning approach that leverages the contextual and the linguistic features to unify these extracted part names. It's only for the part names. So it has 3 steps: unification. What it does is, given a part name, a part target part like panel, it can discover the variants. Like PANEL, PANAL, it's all kind of variants it can discover if we give a part type, a target. Then the normalization, which basically find out the representative name for them. In this, in our approach, we just pick the one that is very frequent. So if something is not, actually sometimes people write those abbreviations more, often than the corresponding things, right? Because that's easy for them. Right? So we do normalization, meaning like finding the most frequent variant of that, and the expansion. So doing that, we can solve like in the one part target, like one word, right? But we know that part names are multi-word. We need to expand that for normalizing multi-word part names. So our framework looks like that. So we started building our machine learning model with very simple examples. Like we give a pair of words and a decision, like door and OOR, yes. And then door and pour, no, right? So kind of give a pair of words and the decision, whether we need to, we consider them as a variant or not. And from that, we created the model, which given a pair, it decides whether those are variant or not. It's a pretty simple model, but it works effectively. And we have, we tried with different features, contextual features like utilizing the semantic vectors from the different word embeddings, or also lexical features like prefix match, suffix match, those kind of things. And combining both lexical and contextual gave us the better performance there. So we use that model, and as you saw earlier, we have the extracted parts, right? We always try with the last term in the part, which is the part A, whether those can be unified by this approach. Because if 2 parts cannot be unified in the head level, there is no point of unifying in the modifiers level. Because if it's not about, here, we don't want to try with others, right? So we start with the last one in the head level. And then if we are successful on that, we try to, unify in the modifier levels. And we have the algorithm on expanding like from the simple to longer part names as in the paper. But this is the output. Like we have these variants which are normalized to that automatically using that approach. So like anti-skid brake control was normalized name came from these variants using that. So summarizing, we talk about different maintenance text, different knowledge here. And then we talk about extracting part names, right? And some challenges on that, and other type of knowledge extractions. And about like unifying. After extraction, we need to unify, right? So I know we have 5 minutes or so. I think we should have time here. So NLP, natural language processing, is a key to mine this kind of knowledge so that we can utilize it into our processes and products, and for the prognostics and health management of the vehicle, right? And we already successfully developed NLP systems which are deployed in our processes that can extract part knowledge from these records. And like this one knowledge, obtaining human annotated data is very hard. It's really hard in our domain. It's so domain specific and sensitive systems. And incorporating any domain knowledge, like instead of like starting 36 hairs, we can always start with all the hairs that we have, right, in our databases, which is basically utilizing the knowledge that we already have. So in the future, you probably heard about GPT-3 and others, which are very powerful in general English. We are experimenting with few-shot learning, utilizing those techniques to see whether they can help us. Those are not trained on our data set that we know, because our data is private. Do they do equally well as they have done outside? So we are experimenting on that, and building domain-specific pretend model, like Christian mentioned, that we can fine tune to our data set and utilize that, right? So those are also the efforts we are applying. and linking multiple data sources to make the full picture. So we have diverse data source in Boeing. We want to link them through this knowledge, extracted knowledge, and then get the complete picture. So these are some of the future directions that we are trying, and we have so many progress made after we extracted this kind of things, which I cannot share due to the IP issues, but maybe sometime in the future I can share that. Yeah, so with that, I'm done with my presentation, and we are hiring. And please go ahead and try to find jobs that matches to you. And if you're interested in AI, machine learning, data science kind of roles, you can contact me as well, so I can connect you to the right places. Thank you. Any questions?
I was just thinking, like, when you search in Google, like, they have this predictive text coming up, popping up, and you start like writing down with it. Could we now go back and then in the log book, after you start writing, you can populate the possible partner? Have you thought about that kind of using this data to like predictive text in the log book system?
Yeah, that's the question he asked. Can we change when we initially input the records, right? And that's another form, like we can do auto-completion. Like instead, as soon as they start typing, we can suggest things so that they can already select something. That's the future technologies we should be focusing on. But the thing is, we have millions and millions of records already in house. How can we leverage that is another challenge. But that's definitely a good step in the future, and we have already doing some of the efforts on that.
Have you considered applying it to quality data in the factory as well? Defects, text?
Yeah, that's a great question. We have been in touch with the Charleston folks to find out different quality issues there. And it's again like a separate whole language. It's not like this what we show what I showed earlier, right? And definitely part names are easily extracted, but they have other different metadata that we need to mine. But which needs the training examples. If we have the training examples, we can do it. But the thing is, how can we minimize, right? So some of the techniques definitely can be applied there, but some needs the training examples.
After after this normalization stuff, it seems like you have a rough hierarchy where you have these heads and then the modifiers. You thought about trying to create a richer hierarchy? Is that something that's relevant?
Yeah, there's a great thought, and we have discussed about that. Like when they write the modifiers, they don't write in the order. Like left main landing gear and then left landing main gear, can be found here, right? So we talk about how to organize this extracted knowledge into hierarchy so that we can use, and we have discussed about some of the approaches here, and definitely relevant to us.
Have you been working on algorithms to do this automatically?
Not yet, but that's on our mind, but we have not actually started working on it. But that's a great thing, because we need to organize it, right?
Yeah, so for kind of deployment, do you see this work coming into like a unified model that can be applied to like an entire business segment, like commercial airplanes, or is it going to be more, these are the structures and the frameworks that work, now it's down to business segments and functions to train and implement their own models?
Yeah, I didn't talk today, which I think probably another topic is, we build these models, right? But in the end, we need to deploy. And in the deployment time, we have this discussion like, can we make per model, per ATA? Because making model per ATA is good, very precise, but we have so many models now, right? And in your questions, how can we deploy these to the actual systems? And we have some centralized data sources where these different records are collected, and we are talking with them to kind of export our results there so that anybody can utilize it. But like there are different interests. Somebody would like to have their own, so there are several issues we need to face. But our approach there is have a centralized place which already actually is storing records, and also the output that we predict, so that those can be leveraged.
Were the two examples you showed kind of outliers or one deployed in different segments other than the landing gear doors that it performed as successfully?
Oh, no, like I picked the landing gear and door because one is from the system side. The landing gear is a part of the systems, right? And the door is the part of the structure. So we picked two ATAs to represent those different things, right? So, and it shows that the method that I presented works for the system side as well as the structure side.
Thank you for your time. Thank you so much again.
Thank you.